So the first system is pumped hydro. We're gonna store the energy as potential energy. This is actually exactly how the PSO, the company in Oklahoma that we have over here, is storing their extra energy somewhere in Virginia, because they don't just run in Oklahoma. They have Oklahoma and like a bunch of states next to each other. So in something, I think in West Virginia or uh, nearby that place, they have a lake on top of a mountain, and down there's a river or the lake downstairs, and they have a pump system over here. And when they have extra energy and no one is using it, then they turn this as a pump, and that pump take the water all the way up and storing it in this place. Now when it comes to the peak load and people are asking for a lot of energy and their power plant cannot respond, then they let the water go down, and then they let it go through a turbine over here, and that turbine run a generator, and you get the electricity that you need. Okay, so they are really lucky that they had this place and they can store the energy back and forth like this. If you are not lucky and you don't have a mountain in your place, what you can do is you can take the water from the lake. You still need lake for hydro, pumped hydro, a lake or a river or something, and then you build a reservoir down in the ground. Of course, this would be way expensive, because rather than just a pipeline going all the way up to the top of the lake or top of the mountain, you need to build the lower reservoir, right? And you need to build the power plant or the pump slash turbine inside this place, right? So that could be expensive. But the point is same thing. What really matter is the delta Z. So the potential energy on the top is mgz, and the potential energy over here is mg, and depending on where is the Z. So if you think this Z is 0, then this is how much you are storing, delta Z. So mg delta Z, right? So if I ask how much potential energy we can store over here, that's as simple as mg delta Z, right? Delta Z is the difference between them, and m would be the mass that we can store in that lake. The second system is same thing but with air. Okay, so compressed air energy storage, CAES system. So that compressed air storage, the air, you cannot store potential energy in air because its density is so small, right? It's not, you cannot just put it in elevation and expect the air here have one potential energy and here down there has another potential energy. Yes, it does, but the density is very small, so that amount of energy that you're storing is almost nothing. So, but they can store in enthalpy, right? How is that done? So remember, the enthalpy is U plus P over rho. So we can have a compressor over here and a turbine over there, and we should have an energy storage place down there, or like it's just like a big seal place. Think about like an old mine that people finish using all the coal in it, so they can seal it, and then we can use it for that big volume. We can use it to store compressed air into it. Okay, the emphasis is not that it's down there. The emphasis is that you can basically put it under pressure. Okay, and so when the compressor, when you have extra energy, that motor slash generator, just like in the same like in the hydro pumped system, you will turn this into the motor mode, and he will run the compressor. The compressor will compress the air, and you store it over here. And in the peak load, when there is like the demand for energy, you let the air go through that turbine, and the turbine run this guy in his generator mode, and you'll end up getting electricity out of it. Okay, now what is that thing over here? Anyone? So what are they trying to solve? So when we compress air, let's plot this on a TS diagram. Here is B ambient, and here is B storage, right? And hopefully you wish that you will go isentropic to S, but in real life you will go over here. And this is said because the ideal work was way smaller. It didn't take that much energy to store the air, but the actual work is way bigger, right? So the actual work would be this. Let me clean the way. Right? So this is work actual, and this is work ideal. And the difference between them, this isentropic efficiency of the compressor, is work ideal over work actual, which translate into delta H over delta H, right? Delta H isentropic over delta H, which translate into Cp T2S minus T1 over Cp T2 minus T1. And it's a good assumption to assume constant Cp, so the isentropic efficiency of the compressor will translate to T2S minus T1 over T2 minus T1. And since this guy is less than 1, that tell you that T2 obviously would be way bigger than T1. Now the sad news is that high temperature that will come out from the compressor, that air is hot air, he will come over here and he will lose his temperature to the wall, right? It will dissipate. He will not store his temperature. He will maintain his pressure. So you are thinking that you are storing the energy in the enthalpy, but this U, the U is CVT. As the temperature drop, that U will drop, and so you will only have the P over rho, but you will use your temperature. So how do you solve this problem? You don't want the temperature to lose. You don't want to lose the thermal energy of the compressed air. So what they do is they have thermal storage material over here. Think about like beads that can get hot and can arrest the temperature. Okay, so like phase changing material. Those could be bead of wax or something that when the air goes through them, it melts, and they stay hot. But with this phase change, they basically store the energy, and then when the air goes through them, he will cool them and get the energy out of them. So when it's time to start running the turbine, he will be able to, as much as possible, stay over here. Maybe he will cool down a little bit if we don't do a good job, and he will expand. And he will expand. Ideally you would like this to be 3s, but in real life it will end up going like this. Okay, so again the actual work that you'll get from the turbine is way smaller than the ideal work that you expect, but that thermal storage allow you not to drop too much. Okay, imagine if you drop all the way to be ambient, it would be disaster, right? You will not get that much energy. So that's what they are trying to do by trying to capture the thermal energy over here and giving it back to the turbine when it's time to generate the power.